Hello everyone. Today we are going to see one type of differential equation. We know that there are many types of differential equation like ordinary differential equation, linear differential equation, partial differential equation and so on. Today we will focus on what is exact differential equation and what is the format of that equation and how to get the solution of that equation. Okay, so we know that differential equation, it is an equation which involves differential coefficient, that is derivative of dependent variable with respect to independent variable. So you can see all these examples are of differential equations. Out of this, what is exact differential equation? We'll see on next slide. Also, we know that the degree and the order of differential equation. We know that the order of differential equation is the order of the highest derivative, also known as differential coefficient, present in the equation. Mean to say, if dependent variable is differentiated with respect to independent variable one time, then order is 1. If it is d2y upon dx square, then it is of second order, like that. And the degree of the differential equation is represented by the power of highest order derivative in the differential equation. Now we will look at how exact differential equation looks like. So here you can see the differential equation of the type Mdx plus Ndy is equal to 0, where m and n are the functions of x and y. This equation is said to be exact if this condition is satisfied, that is partial derivative of m with respect to y is equal to partial derivative of n with respect to x. If this condition is satisfied, then corresponding differential equation, which is of the form Mdx plus Ndy is equal to 0, is called exact. Once we get its nature, that is exact, then we solve that differential equation with the help of this formula. It contains integral of m part with respect to x, treating all y as constant, plus we have to take all the terms of n which are free from x. So the pure term of y will be integrated here with respect to y, and their addition is equal to c, provided that given differential equation is exact. So let's see few examples on exact differential equation and how to solve them. Solve
y square e to the power xy square plus 4x cube dx plus 2xy e to the power xy square minus 3y square dy is equal to 0.
So this is of the form Mdx plus Ndy is equal to 0. So first of all, we will see whether this differential equation is exact or not. For that, we need derivative of m, of course partial, with respect to y. So differentiating m with respect to y, where m is
y square e to the power xy square plus 4x cube and n is 2xy. Yes.
now differentiate m with respect to y, so it's u into v form. So we'll have u into v. So y square as it is, derivative of e to the power xy square is e to the power xy square into derivative of power, that is 2xy. This is with respect to y, plus e to the power xy square as it is into derivative of y square, that is 2y, plus 4x cube is free from y, derivative is 0. Similarly, we have derivative of n with respect to x partially. So again x and e to the power xy square is in product form, so 2y outside as constant, and we use u into v form here. So x as it is e to the power xy square, that is derivative of e to the power xy square is e to the power xy square into derivative of xy square is y square with respect to x, plus e to the power xy square as it is, and derivative of x is 1. So if you simplify this, you get a 2xy cube e to the power xy square plus 2y e to the power xy square. Whereas here you get 2xy cube e to the power xy square plus 2y is inside, so 2y e to the power xy square. You can see these two quantities are equal. It means partial derivative of m with respect to y is equals to partial derivative of n with respect to x, and it implies that a given differential equation is exact. Okay, so once we know the differential equation is exact, we know how to solve them. So first we'll take the integral of m with respect to x, of course treating all the terms of m with respect to x as constant. treating all the terms of y in m as constant. So this is integral of y square e to the power xy square plus 4x cube dx. So y square is constant. Integral of e raised to xy square is e raised to xy square upon derivative of power, that is y square, partial derivative, plus 4x cube with respect to x gives us 4x raised to 4 upon 4 plus c1. So cancellation of y square here. So we get here e to the power xy square plus x raised to 4 plus c1. On the same line, we have integral of now terms in n which are free from x. So only pure y terms to be taken from n. So first term contains x, so we will not take it. So but only minus 3y square is the term which contains no x. So this will be integrated with respect to y. So this gives us y cube upon 3 plus say c2. So 3 cancellation. So finally we get minus y cube plus c2. Therefore solution is given by addition of this 1 and 2. So it gives us e to the power xy square plus x raised to 4 minus y cube is equal to c. Now this c is nothing but the combination of c1 and c2. So this way exact differential equation can be solved. So first we have to check whether it is satisfying the necessary and sufficient condition dou m upon dou y and dou n upon dou x are equal. If so, then we integrate m with respect to x and the terms in n free from x with respect to y and just add them. Another example of same type. This example is also of Mdx plus Ndy type. So we'll write M first. Now we will go for partial derivative of M with respect to y. It is 1 plus 1 by x is constant, partial derivative of y is 1 plus cos y's derivative is minus sin y. Whereas derivative of n with respect to x is 1 plus derivative of log x is 1 by x minus sin y is constant and derivative of x is 1. So you can see these both the things are equal. Therefore, dou m upon dou y and dou n upon dou x are equal. Implies that differential equation is exact. So we integrate m with respect to x. So we have y plus y upon x plus cos y with respect to x. So y is constant, its integral is y into x plus y is constant, integral of 1 upon x is ln of x plus cos y's integral with respect to x is x cos y plus c1. Okay, integral of terms in n which are free from x with respect to y. So is there any term free from x? First is of x, second is of x, and third is also containing x. So there is nothing. So it is just integral of no term or only dy. That's why it is c2. Therefore, solution is we'll have xy functions on left side and all constants on right side as c. So this is final answer for given differential equation. We'll have one more example to fix the concept. Mdx plus Ndy form is already there.
So here m is 2xy minus sin x and n is x square minus cos y.
Let's have derivative of m with respect to y partially. It gives us 2x minus 0 because sin x is a function of x. Derivative of n with respect to x is derivative of x square, that is 2x, and cos y contains no x, so derivative is 0. implies that dou m upon dou n upon dou x, and it further implies that given differential equation is exact. Once we know the exact form, we integrate m with respect to x. So we have 2xy minus sine x, its integral with respect to x. So it gives us 2 into y, and integral of x is x square by 2 minus integral of sin x is minus cos x, okay, plus c1. So it can be written as x square y plus cos x plus c1. And the terms in n free from x with respect to y gives us, now there is a term which is free from x is minus cos y. So minus cos y dy. We know that integral of cos y is sin y, so it remains minus sin y plus c2. Therefore, solution is addition of this 1 and 2. So it is x square y plus cos x minus sin y is equal to all the integral constants collected together. So this is our final answer. So this way we come to the conclusion that how to solve exact differential equation, and very first how to check whether differential equation is exact or not. So before that, our differential equation must be in the form of Mdx plus Ndy, where m and n are the functions of x and y. In next lecture we will see what if the differential equation is non-exact, how to solve them. Thank you once again.